All right, this is Thursday, December 10th, 2020, Aerospace Engineering, a reteaching of how to find reaction forces on truss structures. I'm going to cheat and use graph paper all the time. If I don't use graph paper, then I'm going to be forced to use a protractor and use trig functions all the time to measure angles and distances. By cheating and using the graph paper and always selecting to have my members be integer units of the graph paper spacing, I will have the freedom of being able to slide any force along its line of action for any situation so that it always ends up being perpendicular to the distance from the axis of rotation to the point of application of that force. So I'm starting off with a beam that is 5 units long. We'll say that each unit on this graph paper is 1 meter. I'm pretty consistently choosing to put my pivot on the left of my diagram and my roller on the right. Now, a roller can really only transfer forces perpendicular to the roller. If I were to try to push on the roller left or right, it would roll. So that we don't want it to roll. So it's just there the way you have your pen sitting on the table underneath your calculator. Okay, so you don't want your calculator rolling on the pen. You want it to just sit there stationary. We're trying to solve for a non-rolling bridge. So the only forces are allowed to act perpendicular to the solid surface of contact in the situation of a roller. For a pin, we not only have forces that can be applied, let's say vertically, but it can also withstand forces being applied horizontally as well. These, I guess you would call them, are the degrees of freedom for these 2 points. So the roller can only handle perpendicular to the surface, and pinned can handle all directions acting through this point. So what I've done is I've said, okay, I'm going to apply a load of 100 units, we'll call them newtons, at a point that is 1, 2, 3 meters to the right of my pivot point. And the challenge is, well, what are all the reaction forces? Here are the equations we always use. The sum of all the forces in the x direction must always add up to 0. The sum of all the forces in the vertical direction, or y direction, must always add up to 0. The sum of all the moments about any arbitrary axis of rotation that you choose, which in physics course I would say is the sum of all the torques about that axis, have to add up to 0. And to calculate the moment or the torque, the formula is it is a cross product of 2 vectors. The first vector, r, and order does matter because the commutative property of multiplication for vectors does not apply. The first vector, r, is the distance measured from whatever axis of rotation you choose to the point where the force is being applied. In this example, I'm choosing to put my axis of rotation at the pivot point, but that is arbitrary. I could have put it anywhere I want. And mathematically, that is fine. It's like, where do you want to put your origin when you're doing a race with someone else? Does it matter if you say the reference point is in New York State instead of in California? After you each run 1 block, you still know who the winner is. So the same thing is true for all of these equations. It doesn't matter where you put the origin for all the horizontal forces. Wherever you put the origin, they have to add up to 0. Wherever you put the origin, they have to add up to 0. Same thing for rotation. Wherever you choose to put the origin, they still have to add up to 0. The formula is the magnitude of the distance from your selected axis to where the force is being applied times that force. So I'm putting it as absolute value just to say, look, it's the magnitude of the force times the sine of the angle between these two directions, and always from this first direction to this second direction, always in that order. From to, if it goes counterclockwise, then that is a positive angle. If it goes clockwise, that is a negative angle. And a few other things. The sine of 0 degrees is 0. The sine of 90 degrees is 1. And we're going to be choosing to slide the forces so that the angle becomes 90 degrees or negative 90 degrees. And the sine of negative 90 degrees is negative 1. So we're going to be choosing to cheat like this all the time, but it's just a math trick I'm using to make your life simpler as much as I can. All right, so back to the simple warm-up problem, and you'll need your calculators, right? If I have 100 Newton load being applied vertically at 3 meters from the pivot point, first of all, I'm going to tell you, I do tend to pick the pivot point to be my axis of rotation practically all the time. Now, for any one analysis, you can shift that axis of rotation to solve a problem at some other point. And I'll show that hopefully later today. But in general, I'm going to start off, here's my axis of rotation. So R, the distance from this axis of rotation to the point of application of the force in this example is 3 meters. The force is 100 newtons. Now the angle always starts off with the direction of R as being 0 degrees. In this particular drawing, R happens to go along the positive x-axis. That's just coincidence. We don't care what the direction is of the positive x-axis. What we really care about is what is the direction of R. And if R starts off by going horizontally to the right, whatever direction R is pointing, we're going to define that as being 0 degrees when we turn into the direction of F. Remember, this angle theta here is not the sine of the angle of F with respect to the positive x-axis. It's the angle between the direction of R and the direction of F. All right, so once again, R is going horizontally to the right, so I define that as being 0 degrees, and I observe that I am turning clockwise 90 degrees to point into the direction of F. So theta, being clockwise, is negative 90 degrees. You can do this one in your head, right? The moment, therefore, is 3 times 100 times negative 1. I get negative 300 Newton meters. Just a reminder, although a Newton meter is also a joule of energy when we calculate work, when we talk about moments, they are never called joules. They're always called Newton meters or whatever units you're using of force and distance. Inch, pounds, Newton, centimeters, never joules or anything else like that. Okay, so at the moment, there is this one twisty force caused by this force trying to make this beam rotate to fall down underneath the roller. It's not allowed to move. The roller must be counteracting on that moment. Right. I'm not worried about the forces first. I'm worried about the moments first. And the moment is, now I have a new R. I suppose I should change colors of my ink. Good thing I'm recording this, right? So the new R is from the same axis of rotation. I can't switch it in the middle of a calculation. To the point of application of the reaction force going through the roller, which I hope you recognize is going to be an upward vertical force out of the two choices. The roller is going to be pushing up on the beam. In fact, I'm not even sure a roller can pull down on a beam. I mean, think about it. If I put my calculator on top of my pen and I lift it up, the pen doesn't keep it from going up. So I'm not even entirely convinced that this is an option. Sorry, I just wiped this out. That this is an option when we consider the degrees of freedom acting through a roller. If you know better, let me know. I've always avoided giving you problems where the roller has to pull down on the beam. I've always given you problems where, if anything, it pushes up on the beam. Okay, so to calculate that reaction force, I'm going to sum all the moments about this axis of rotation so that they add up to 0. Great. Well, this new distance is now 5 meters. So in this new calculation, R equals 5 meters. The angle, I'm going to choose it to start off. Again, R happens to be horizontally to the right, and the reaction force through the roller is 90 degrees in the counterclockwise direction. So the angle is going to be positive 90 degrees. The moment has to cancel the 300 Newton meters caused by the load acting at 3 meters. So the moment must be positive 300 Newton meters. And hopefully you see this as a Math 1 problem that says the only thing that's unknown is the reaction force through the roller. And I'm going to see what nomenclature my stuff uses. Okay, so as a habit, we'll call this thing the pivot point, point A. We'll call the roller point B as far as labeling vertices go. And so this was the load, and this is going to be the reaction force through B in the y direction. And that is our only unknown. In the equation, M equals R cross F, we have 300 Newton meters is equal to 5 meters times the reaction force in the y direction through vertex B times the sine of 90 degrees. Okay, well, so I think your answer is 300 divided by 5. 60. I did that one in my head. Hopefully I got that one right? Yeah, 60 sounds right. 60 newtons. Okay, so let me like redo my drawing. my skills are so bad, I'm going to use a straight edge, right? 1, 2, 3, 4, 5 meters again. Here's the pivot. Here's the roller. Here's my 100 Newton load. And now I know that the reaction force is, and this is not to any real scale, this is 60 newtons pushing upward on the beam at the location of the roller. Of course, I'm not done, but I at least have one reaction force now. All right, way back at the beginning, the very first thing I said was the sum of all the forces in the horizontal direction have to add up to 0. And then after that, the sum of all the forces in the vertical direction have to add up to 0. Well, in this situation, the sum of the forces in the horizontal direction are 0 because there are 0 horizontal forces. Ta-da! I could check that one off. The sum of all the forces in the vertical direction do not yet add up to 0. I've got 100 newtons going down. I've got 60 newtons going up. And so now I do sum of all the forces in the vertical direction. And clearly, out of the 4 choices acting through the pivot, there must be a vertically upward force canceling 40 newtons of downward force. And I guess I would call that the reaction force through A in the vertical direction is 40 newtons. All right, check and check. By the way, in case you've forgotten, because I chose this pivot point to be my axis of rotation, the distance from the axis of rotation to this 40 Newton force is 0 meters. And what does that do? Well, in the formula, oh man, where do I put that one? Sure, here. In the formula, if the distance is 0, then the moment is 0. And this makes no contribution to the twisting force of this beam. I told you before that you can pick any point to be the axis of rotation for your analysis. What if I put it over on here underneath the roller instead of underneath the pivot? Well, then we would have had 100 times 2 is 200 Newton meters. Positive, by the way, because now R is to the left and changing to F is a positive 90-degree change. So this moment is positive 200 Newton meters relative to this pivot point underneath the roller. Sure enough, 5 meters times 40 newtons, 5 times 40 is 200. R is to the left. The angle is a clockwise 90 degrees to get to the 40 newtons. That means it is a negative moment. Negative 5 times 40, 200 Newton meters. Negative 200 Newton meters cancels positive 200 Newton meters, and ta-da, the moments add up to 0. Any arbitrary axis of rotation. I could have picked the very middle of the beam to be my axis of rotation, my pivot point. If I had done that, it would have been 0.5 meters times 100 newtons is 50 Newton meters negative, right? Negative 50 Newton meters. about this axis. And then I would have had more of a math challenge, right? All I could say right now is that 2.5 meters times the reaction force in the y direction as a negative moment plus 2.5 meters times the reaction force at the roller, opposite sign, these three moments add up to zero. You have one equation, two unknowns. So then you would use a second equation, reaction force at A plus reaction force at B plus or minus 100 newtons add up to zero. And then solve by substitution. See, that is the most work. What we did was equally easy this way or that way. All right, take your 3 minutes break.